Okay, so what would you like to cover in our office hours?
Okay, there was one question let me pull them up. There was one question that I'm still not entirely solid on that's actually from a couple sessions ago.
Okay.
And I never was actually able to finish that homework.
Okay, which one would that be?
Now.
Which session?
In, I think it's Beams 3 or something like that. I'm going to find it right now.
Beams 3 would have been session 13, maybe?
Here we go. Session 12, Beams 2, actually.
Okay, session 12, Beams 2. All right.
Yes.
All right, let's see if we
This
can
one's
find it.
sucked.
Which question?
Question 3.
Okay, session 12.
Even with the guides, I still wasn't able to get it.
Okay. Let me see. And then it's question 3. Let's see here. That's question 2. And yes. Okay. Yes. This is a tricky one. Okay, so let me see. I'm going to look for my notes too to make sure I can go through this correctly. Let's see here. Okay. All right. Let's see if we can. So this was question number 3 in here. Nope. Okay, that's question number 1. Here we go. All right. All right. So let's see if we can go over this problem together. And essentially, this problem has a applied force, right? And an applied moment. Okay. And we're going to suspend reality just for a little bit here, in that this piece on the right, I'm going to put a ruler, but it's possible that there could be right? There could be a force that picks it off the ruler. Okay, but if we have things planned out correctly, it's probably not going to do that. And in fact, part of the condition that we put on this problem. Okay, well, let's draw it out, and then we'll talk about some of the conditions and things. Is that I think it does actually still maintain. No, I think it actually does have to pull down. It still has to pull down. Yeah, the way I've got this thing set up, because what you've got here is an MechMat like that, and we've got a force. And I believe this is going downward. Is that right? Let's see. Force F-ab downward. Like that. Okay. And this is a distance. It's maybe not quite to scale, but this is L over 4 from that side, and this is L over 4 from that side. Correct? Okay. And what is the question asking? It's asking us, what is the maximum bending moment along the beam? Okay, and the idea is that we're supposed to use our understanding of how to make shear force and bending moment diagrams to be able to calculate this out. Okay, Yeah, this is not a trivial problem. It looks simple, but it's not that simple. Okay, so the kind of maybe the first, oh, and there's a condition, right? I think there's a condition here that m app over L is greater than f app over 4. So, and then we say that m app.
I had a quick question.
Uh-huh.
How exactly is MF working on the beam? Is it exactly as we see it, as there's a counterclockwise moment twisting around that point on the beam, or is it going around the beam?
It's, imagine that you're moving along the beam and you stick a screwdriver in that location and I twist like that. Okay,
Got it.
that's what this M app really is.
God.
Okay, so it's probably a good idea to start off thinking a little bit about external equilibrium. All right, there's different ways, and I think even in the session notes I do it a little bit differently, but let's go ahead and think about what external equilibrium might look like. So for that, we'll draw the beam again, and in this case we have our M app again, and we have our F app, right? And then what are we missing?
The reaction forces.
Correct. So here we can kind of choose, right? F app and M app are given in terms of the directions, but here we can kind of choose. And I'm going to choose the following, okay? And this is where we suspend reality slightly, because we're going to say that the reaction force on the right is going to be pulling down on the beam, but this is a roller. And this, you know, you could pick these to be the opposite directions, but you kind of have a sense that it's possible that this M app could kind of pull up, right? If I'm twisting, if I have the screwdriver in there and I twist, it's possible that it could cause there to be a pull up, and so maybe I'd want R to like pull it down to keep it from doing that.
Right. That's why you were saying earlier it doesn't have to be a roller.
Right, exactly. That's why we're suspending reality, because I mean, I could do 2 pins, right? But then other people will be like, well, you know, you got 2 pins, and so this is not free to like roll around, quite literally, and so that can be a problem. So here, all right, what we do for the external equilibrium is some forces and some moments, okay? And so if we sum up the forces, oops, that's moments, sum up, we'll say forces and sum up the moments, right? And for this moment thing, it's not bad to pick a location. So we'll go ahead and I think I picked earlier the left side. Yeah. So the forces. Okay, so taking this one, that's gonna, we have an RL minus F app minus RR is equal to 0. Okay. And on the right side, or on the for the moments on this right equation, okay, this taking this over here, let's say that we have our and we're doing it at the left, right? So we're at this location, so we don't have an RL, but we'll have a kind of a minus F app L over 4. Okay. And we'll have a plus M app. Okay. And then we'll have a minus RR L. Is this, I think this is right. Okay, equal to 0. Yeah. So here we have two equations and we have two unknowns, right? Because MAP and FAP are given to us, but we don't know what the reaction forces are.
Right.
So at least we can figure out what the reaction forces are here. So for that, the reaction, we can write that RR, right? This will come out just from this equation because these are knowns. We can say that this is going to be equal to MAP over L minus FAP over 4, right?
Over L minus.
Yeah, so this is going to be MAP over 4 okay, minus, or no, MAP over L minus FAP over 4. Okay. And if you look, right, this condition that we had right here, what does this kind of mean? This means, okay, I'm saying MAP over L is greater than FAP over 4. So if you look at this, now we're saying that RR actually is positive. Okay? And that is meaning that, yes, our suspension of reality
Was correct.
was forethought out. Okay, was planned out. Okay, so and then we can figure out what RL is. Okay, based on this equation here. So we have RL, right? It's going to be FAP plus RR. So FAP, right, can knock out a lot of this over here, the minus. So we're going to have a MAP over L plus 3 FAP over 4. Okay, so we've got now an opportunity to look at what the boundary conditions are. Okay, at the left and the right. Now, when we do that, so now we can take a look at the BCs, right? I don't know. We have fun with colors. There's so many colors here. We haven't used blue. Okay, so let's look at the BCs. At the boundary conditions. On the left side, okay, we have the opportunity to write this little squiggly, and we'll say this is the left side, so this is going to have an RL down here. And then using our convention, right, we have a V and we have an M. Okay, and they're at the left side. Okay. So at the left, right, so here, what does it mean? It means, well, and maybe I should write left side. Right, so here we're going to have V equals RL, and we're going to have M equals 0. Okay, and then at the right side, we can have a squiggly, and we can have an RR like this, and we have our convention with V going up and M going like this. Okay. So at the right side, conveniently, V is equal to RR and M is equal to 0. Okay?
Wait, do I have that written down? I do.
You do.
I do.
All right. So we've kind of done nothing new here
Yeah.
at this point. This is all da da da. Okay. And we can go ahead and start. It's probably not a bad idea to start drawing out the stress, or not the stress strengths, the shear force and bending moment
Yeah.
plots, right? or graphs. So let's do that. Let's go ahead and we'll do it in black. I'm going to make here a shear force. Yeah, and this is going to be X, right? And then this goes to some L, 0, and I'll make a bending moment. And it's kind of helpful that I know already, more or less, what's positive and negative. Okay. And this is M. Okay. Otherwise you just got to take a lot of space and may give some room for like a negative if it goes a lot negative. All right. But here, we're safe. Let's take a look at now our differential integral relationships, right? So the first one that we know and love is dv dx is equal to w.
Right.
Okay. And in this case, there's no w, right? So w equals 0. So if I integrate this, right, I'm just going to get a constant, essentially, right? Now, this is interesting in that it's a constant, has 0 slope, is a better way to look at it.
Yeah.
But can that constant change?
Yes.
Yes, because we have concentrated transverse force being applied at a given section, right? And so we also can kind of see something interesting may happen at L over 4 and at 3L over 4. Okay, so let's also go ahead and let's mark those spots out here. Whoops, not 3L over 4 there. I'm jumping ahead. Okay, and this will be like 3L over 4. And we'll just mark those on the bottom plot as well. Okay, so we know it's a constant. We know we have an F app, right? And this F app, okay, is going downward, right?
Mm-hmm.
So the delta F, like, whoops, stuff, okay, sorry. So the delta F, okay, so this is one thing. Well, actually, sorry. Yes, the delta F is F app, but it's really the delta V is going to be minus F app at X equals L over 4. How did I do that, right? I remember we have the relationship delta V is equal to F app, right, at a concentrated location. But since F app is downward, we can say it's going to be subtractive.
Right.
Okay? So I don't worry about this until I get to the L over 4, all right? But what do I have? I have at the left side, V is equal to RL, okay? And we can say that means over here, maybe I'll use a different color. I don't know, what do we want to use? We can use this kind of interesting blue. Okay, over here, that means that we start off at RL, right? Because that's what it's equal to right here.
Mm-hmm.
And then it stays flat until we get here.
Right.
Okay? And then there's going to be a discontinuity, all right, equal to F app. Does RL, or does when it drops down, Okay, does it stay positive? You might ask yourself the question, or does it go below? And the answer is, well, let's take a look. M app over L is supposed to be greater than F app over 4, right? So this is greater than F app over 4. So, F app over 4 plus something greater than F app over 4 plus 3 F app over 4 means it's going to stay positive.
That makes sense.
Okay, so this, we can say that this will drop down to this value.
Right.
Okay, and we can call this, I don't know, what do we want to call it? Well, actually, we kind of know what it is. It is RL minus F app, all right? All right, so we'll just call RL minus F app, like that. And it drops down to there. Okay. Now, we still say it's constant, the V is, all right? So, and there's no other discontinuity, or there's no other concentrated force applied. So that means that it just stays flat until it gets to the end,
Okay.
right? So actually, I know what that value is, because over here, that's just equal to RR.
Right.
Right, so that's RR like that.
And the M app contributes absolutely nothing to that because all it is a moment.
Correct.
Got it.
Okay. Now let's take a look at what's happening with the moments. Okay. Well, there are a couple of things. Let's change the color again. Red. If we now take a look at the dm dx equals v, right? Then we would say that, okay, we have an integral of dm, right, is equal to integral of v dx. Okay. And since this was a constant, since this is a constant, this means that m is going to equal some type of sloped line. Okay, and it's got some slope that we have here. And now we look at it and we say, oh, it's always positive. Okay, it's always, the slope is always positive because v never goes negative.
Right.
All right, so this is kind of interesting, right? We also know that we have this MAP, right? And this actually contributes a negative, correct? So we have a delta M equals minus MAP at 3L over 4.
Wait, why is it negative? It's going counterclockwise.
Yes, but when you do the derivation, this is the one, right?
This is the reversed one.
This is the
Right.
reversed one, right?
Oh, okay.
Okay.
So it's reversed if what? It's happening directly on the beam instead of about the beam?
So this is an externally applied moment.
Right.
Okay, so the how do you say it? It's we think of conventions for the insides, right? And if we do the equilibrium on this, which we did in class previously, you'll see that given the conventions that we use internally, it's going to result in a clockwise MAP, resulting, if you're going from the left to the right,
Yeah.
that's going to result in a positive jump. Okay? So you can go back, but this is truth. Okay, this is truth. Okay, so some interesting things are going to be happening here, right? So we have a sloped line, and we have this discontinuity. All right, and we also, oh, I guess I should have drawn this nicer. This, by the way, this is from 0, so this is going across. At the top, I was just up here. Okay, so we also have a drop, right? We have a drop in the shear force, right? And that shear force is determining the slope. Okay, so what are we thinking here? We're thinking, well, let's go back. The boundary conditions say that we have m equals 0 and m equals 0, right, at the left and the right. So if we, yellow is kind of hard to see, but oh well, right? We know this is where we're going to end up at those two spots.
Yeah.
Okay? We also know that we have positive slope throughout. Okay? And this has a higher slope. So let's just say that we get up to some location here, like that.
How'd you determine that?
So I'm just saying it's a positive slope, okay? And it has a lot of positive slope because this is more positive than this.
Oh,
Okay?
So
But so that says something about what happens afterward actually. There's no discontinuity, so there's still going to be positive slope, okay, until I get up to this location. Like this. Okay? There's a discontinuity in the first derivative, right, which is the shear force. Okay? But we are interested in figuring out again, what we want to figure out where we are.
Yeah.
Okay. Right now, we're just talking about like just graphing it. Okay.
So both endpoints in the M graph so far are not defined.
Correct.
Okay.
Okay, and then we're going to do one more that's not defined either. Okay. Look, this we said has to be greater than 0. And in order for us to maintain a positive slope, right, and it's actually the same slope here, and in order for it to be greater than 0, that means that it has to have the same slope and be underneath. That's not exactly the same, but let me see if I can do a little bit better. You see this? Does this blow your mind?
And that has to happen because it's still a positive slope, but has to reach 0, right?
That's right.
Yeah, that's weird.
Okay, so now we know that this is a delta. So at least we know this is the delta m, and this is going to have some amount m app. Okay, that's just the jump.
Oh, I think I understand why that happens now. Because it's a moment acting on the beam, on the left side of the moment it's kind of pushing down, on the right side of the moment it's kind of pushing up.
Yeah.
That makes sense.
Yeah. So I'll draw it this way so that it's kind of like funner. So this is the m app. Okay.
Okay.
Now, I think, in class I said something about, okay, typically when you're trying to find the maximum, you look for when the derivative crosses 0. And anyway, that's a boo-boo on my part. I didn't remember the problem super well. Because in reality, the derivative of this does not cross 0, right? This is always positive.
Yeah.
So we're just looking at when it, what it's going up to, okay?
Right.
So now there are a couple ways we can solve for what this maximum is, all right? One way is to integrate here, and then integrate again here, and then figure out where we are over here, okay? And that's probably not a bad approach. Okay, the other way is to say, okay, I know what the slope is here. I figure out what I get down to, and then I jump up by m app. Okay, so let's do it. I think in the notes I did it the other way. So I think I went from the left and going to the right.
Yeah.
Let's now see if on the fly we can do it going from the right, left. All right.
Okay.
So what we need to know is we need to know the slope here. Okay. So the slope there is RR.
Oh.
Right?
Right.
That's what the slope is. Okay.
Okay.
So, and let's make this now a Mach. We're gonna call this a Mach x2. Okay, because it's really, you know, x2 is really you can think of it as, you know, because x2, if x2 is equal to 0, that's really x equals 3L over 4.
Yeah.
Okay, so if we want to map them to each other, right, we could say that x2 is or x2 plus 3 over 4 is equal to x, right? But that's kind of that we don't really need to know that. That's just how we're thinking about it, okay?
Yeah.
But what we are thinking about is what is the slope. So here we have that an equation for, so now m as a function of x2, okay, we can say is going to be RR, okay, and RR is this kind of big thingamabob here, right? That's like kind of not a friendly expression, so let's just leave it as RR, x2, and we're going to call, how many constants do we have? Let's just call this, for lack of, I mean, I guess I can use C because I didn't really use C anywhere, but let's just call it C2, okay? Because I'm doing an indefinite integral, right, of the of dm, or indefinite integral really of the shear force, right, which is going to equal okay. So here at x2 equal L over 4, okay, what we need to have happen, what do we need to have happen? We need m of x, or m of that equal to 0. Okay. So we can plug in, right? Let me make sure I have enough space here. You know, I got a lot going on here. We got a lot going on here. But let's just do it, right? So we have RR times L over 4 plus C2 has to be equal to 0. So this means that C2 has to be equal to minus RR L over 4. Okay?
What do you mean by at x2 equals L over 4?
So the distance from this location to this end is L over 4.
Okay.
Right? Because if we go back here, remember we said this is 3L over 4?
Yeah.
Okay. So now, this is kind of fun. We can go backwards, right?
Yeah.
We know that, so at x2 equals 0, we now know that the moment, right, I plug it in, it's going to be equal to minus RRL over 4. Correct?
Yeah.
That's how much we dropped there. So minus RRL over 4. And the max moment is this point plus map. So now we can say that the max moment, M max, is going to be M app plus minus RRL over 4. Now, what is RR times L over 4? Well, let's see. That's this expression here. So multiply by L and minus. Okay, so it's going to be equal to, well, maybe I should write it out. Minus RRL over 4 is going to be minus M app over 4 plus F app L over 16. Did I do that right? Yeah. Okay. So now this expression, okay, if I'm adding these things to each other, minus, yeah, that's, no, did I do the minus still? I did the minus, right? I distributed the minus properly? Yeah. Okay, so this is going to end up being, this minus RRL over 4, this is going to be a 3 M app over 4 plus F app L over 16. Okay, and let me check if this is correct or not. Let's see. Oops, what did I do? Okay, let's see here. Is that right? Okay, actually I have a different I have my expression in terms of RL and RR still. All right, but I believe we did it correctly.
Nice.
Okay, I have to think about. I had to distribute the my MX was out of was.
Yep, we did it correct.
We did it correctly. You got it.
Correctly. Yep.
All right.
I have.
What's up? I can
no
still
idea how
do.
much
I mean,
that word is gonna be.
That's not quite 100% on the fly because I had my notes, but that was still a little bit different. Yeah. So I apologize for any confusion that I caused
It's okay.
with saying, hey, you just did the derivative equal to 0, because I was just looking at it and I was like, oh, that's what you do. No, in fact, that's not what you do here.
No.
Okay.
Derivative equal to 0 doesn't work entirely well because there's so many discontinuities.
Mm-hmm.
I did try and integrate it piece by piece at one point, but I was setting up the integrals completely wrong.
Right. Well, did you see that? We didn't do a single integral.
We didn't.
We just used the graphical method.
And at one point I was doing definite integrals instead of indefinite integrals. I figured integral from 0 to L over 4 of whatever I came up
Right.
with relatively would work, but for some reason I would get different answers compared to if I did an indefinite integral and just use the constant.
Yeah. Yeah. Okay. So this is fun. All right. So now let's talk about. Well, what else do you want to talk about? What other questions do you have?
Let me double check the homework that I
Okay.
did because there were some torsion questions I know I didn't fully get, but let me check this one. I hope it'll be other people here, so I didn't come as prepared as usual.
That's okay. Then I'm looking at the clock.
Yeah.
Hi. Okay.
Oh.
How's it going, Jude? No, you're here. You're in the right spot. So you're in the right spot. So, are people coming?
I think so.
Okay. So we are doing a synergistic thing. In that we're having a lab lunch during office hours. So we've ordered some extra food.
What?
Right? I did a Krisha ordered it? Okay. So we've got some food coming
Oh.
from a Indian place?
Yeah, Indian place.
And is it a vegetarian Indian place?
I don't think so.
You don't think so? Some of it was vegetarian.
Yeah, they have like vegetarian options. I think.
Yeah. So I don't know. So if you want, if you're willing to, you can partake.
I appreciate that a lot because I forgot to take food from home.
Well,
I have a snack in the fridge. and I
this
just-
maybe you're lucky, as long as we didn't, of course, check with anyone's dietary restrictions in the class, but yeah, we're kind of merging those two things together.
This is our class.
Yes. Yeah. And so this is James.
Hi, I'm James.
Hi, I'm Kira.
I'm a sophomore.
Sophomore? Nice. I'll be 2 next year.
Yeah.
That's nice.
Not a mechanical engineer. Not an aerospace engineer.
Yes.
What's your major?
I'm MSc.
Oh, nice.
And physics.
And physics. Yes.
Nice.
So it's a little bit related to mechanical.
I was actually thinking of doing the material science concentration because that's, I work for the advanced materials and structures department I work with right now.
Got it.
And it's pretty cool.
MSc is so cool. I mean, department and everyone's so nice.
Nice. I don't even know if they allow aerospace engineering majors to do a concentration because I know mechs you almost have to do a concentration if you want to do anything.
Yeah, so it's well, aerospace technically, yes, you can do the concentration in energy.
Oh, energy.
If you so desire, or packaging.
Okay.
Okay, so we
yeah.
we don't. It's in the handbook that we do that. Hello, Shane. How are you doing?
Good.
Great. Do you have any questions?
Not off the top of my head.
Okay. All right. Well, we're at a transition point, so we've been working a little bit, and there's also going to be some lunch coming. If you don't have to, but we're having. I how do you say this? I double booked myself, and I was like, how can I make these two things work together? Because I told the lab, yes, we can have a lab lunch, and I told you all that I'd be here for office hours.
Oh, I get it.
So I was like, wait a second, we'll just combine the two.
That's awesome.
So they'll be like having a nice lab lunch,
Right.
and you can have some, and then we'll continue to have office hours.
That's
I don't know. That's like, is that a sickening lab lunch?
I mean, but it feels good. And people can have questions.
Yes, people can have questions. That's right. There was one thing I wanted to talk about though during office hours, since lunch is not yet here.
right.
Okay, I wanted to talk a little bit about how we think about the shear stresses that we map along a beam. Okay, I just need a spot. Where can I put this spot? I don't know. Maybe around here. And this is a little bit on the fly because I was just thinking about it, and well, let's see if it comes out correctly. So what I was thinking about is how to explain the direction of the transverse shear stress or that you might have with a beam. Okay, and so now let's suppose that we have a force P at the end. Okay, and this is X and it's coming off. So if I take a slice here, I'm using my convention, right? I'm going to have a V and I'm going to have an M, like that. Okay. So the question is, how do I think about the shear stress, right? Because now if I explode this guy, oops. Oh no! Speaking of explodes. Okay, hold on. Let's see. I think it might come back. Okay, and I'm looking at that opening, right? So this opening here is this opening here. Okay, what is the relationship? So that's if I have a V across, right? what is the relationship for, let's say, right along the neutral axis for the shear stress there? Okay, so now I even go further and I'm thinking, oh, there's a shear stress acting on this face. I think it's downward, and I draw my little cube. Ah, it's a crummy cube. Still crummy cube. Like that. Okay, you see what I'm talking about? Because this is common. So now I have a stress, right, like that, and I'm probably going to have, you know, to keep everything nice and friendly, you know, I'm going to have oh, that's horrible. I'm going to have a stress like that, and on this face I'll have a stress up like that. You know, on this bottom face I'll have a stress coming like this, or arrows, better said, right? So, you know, what does this look like? You know, and so what we kind of skipped the last time we did this is the basic idea that if you have this beam, the first thing you would do is you would look at external equilibrium. Okay. Right, if I look at external equilibrium, then here's the RL, like that. Now I'm worried, is it going to do its buggy thing? Okay, it didn't do its buggy thing. Sometimes it does another buggy thing. And I have, I'm going to have an ML as there, right? And those are external, and I'm picking those. Those are my options. So in this case, right, we have that RL is just going to be equal to P. Okay? And ML, if this has some length L, okay, you know, ML is going to be equal to PL. Okay, just from external equilibrium. So if I were to cut this thing, right, like we just did essentially, right, then it's not so hard to see that V is going to be equal to RL, and RL was just P. Okay, so when we come back over to this diagram, right, this V is equal to P. And we kind of skipped that last time, and maybe it didn't sit wrong with anyone, but when you draw, so essentially when we draw, for example, a cylinder or some type of beam, right, that's cylindrical in cross-section or circular in cross-section, and I've got an external force, P, acting on the end, okay, it's kind of, you think, oh, it's kind of intuitive that if I then take a slice of this, and look at it, that the shear force of interest, V, is going in that direction. It's going in the same direction as P. Okay, so this is kind of like this is just doing the background work to show that, yes, P is going down, and so V is going to be going down as well. And then now, when I look at the shear stress here, the transverse shear stress, I know that I have some, this is if I zoom in on this, a little element, right? This shear stress, let's pick a different color. That shear stress, tau, and I'm going to say it's max because I've drawn it on the neutral axis, right? So tau max is going to be, if this is rectangular, it's going to be 3/2 times the P over A. Okay, and A is the cross-sectional area. A is this cross-sectional area. Right? A cross-sectional area. Okay. Now, let's say that, yeah, this is still X coming out of the board. Oops, I thought I hit black. This is X, okay? And we'll say that this is Y, okay? And that means that Z is coming out of the board like that. Okay, so this is, maybe I'll draw X like this. Is that more clear? Because it looked like a plus sign. Okay, so now if I want to be more particular about the direction, what would you call the stress acting on this face? Like if I were to generally draw a cube. A shear stress, right? I'm sorry, what would be the subscripts you would use?
X would be tau X negative.
Yeah, right. So the way it's drawn, it's in the negative y direction.
Yeah.
Okay. So I would say this is a tau xy. I would say that tau xy, you know, at the neutral axis, okay, at x equals L, I would say is minus 3/2 P over A. Okay, because if I drew, so let's take this, you know, now we're going to rotate this element. Rotate element, okay, to look at it sideways, okay, then I would have X, well, let me draw it in different colors because that's probably helpful. I would say you have X like this and Y, right? You see we just rotated it, so now I'm looking at this face on this side, okay? So X is that, and then the convention is that this is drawn with shear stresses such that this is tau xy, okay? And this would be tau yx on the top, right? But we know that since it's an isotropic homogeneous material, then it's going to have tau xy equal to tau yx, okay? So yes, I just wanted to point out, and see this is in the opposite direction as this. So this is how, this would be the appropriate, given this coordinate system, this would be the appropriate way to describe the stress on that face as minus 3/2 P over A. Hello, come on in. How are you doing? Okay. So this is just something I wanted to point out, all right, to everybody here. Are there other questions? Okay. Yeah, so we'll go ahead and why don't we go ahead, or we'll pause. We can, do you have other questions?
Not at the moment.
Okay, let's go ahead and pause this and then people can get something to eat. All right.
Hey guys.
Hey.
We have.
Let's see. There was another problem that came up that people were interested in seeing, right?
I was going to ask about the bent pipe problem.
Okay. So this one maybe?
Yeah.
This one right here? Okay, that I kind of glossed through pretty quickly.
Yeah.
Okay.
Don't really know what's going on.
Okay. So I'll start this way and then I'll add some notes to what we're doing. Okay. We have 3 loads that we want to look at in their contributions to the state of stress at this location that we've specified, right? And there are kind of a couple of things that happen. Whenever you have this offset, like you see here, there's going to be the potential for a bending moment when you have transverse loads relative to the beam. Okay, so what does that mean? So that means that Py and Px, in these cases, they can apply essentially a moment or a torque, right, that takes advantage of this leverage, this lever arm B. Okay? And Pz was already essentially applying a moment based on its lever arm A. Okay? So that's kind of what's happening with the bend and with this extension B. Now, if this B were not present, I would just transplant all the purple forces to this location at an offset distance A, lowercase a, from the capital big A. Okay? So that's very useful when we want to look at the contributions of the PX, PZ, PY, okay, in terms of what they're doing to the system without, this moment arm B with length lowercase b. Okay? And in the case of PZ, you can argue that this lowercase b lever arm doesn't really do anything. Okay? Like it's because it's acting along, right? You only get a moment when you have R cross F. And so if the R, right, the vector, the length vector of the lever arm is in the same direction as the force, then it's going to contribute 0. Okay? So essentially what we want to do is begin to look at the individual contributions of each of these forces to the state of stress at A. And to do that, it's sometimes useful to draw the entire cross-section where we've taken a pizza slice, or taken a whole pizza actually out of this beam, and we've put it there. Okay, so we're going to do this a few times. We're going to look at contributions from Px, contributions from Py, and contributions from Pz. Okay. We're clear up to this point, right? Now we get into the kind of the what in the world is happening. How are we figuring out what's happening at A? So for that, let's go to Px. Px is coming out this way, all right? So it's going to make a couple of contributions to the state of stress, or maybe potential state of stress, right? One, before we even do anything over here in terms of the algebra, is that Px, if I were to transplant it over to this intersecting point here, right? So if I got rid of the length of the little b moment arm and I just moved it over here, right? So like I just put a little Px over there, right? Then I would see that it's contributing to a normal stress that's causing this section to want to stretch in the x direction. Okay? So I can think of, all right, what's the cross-sectional area here of the pizza, right? Which would just be the radius, so pi c squared. Okay, and I have a px, so I know that I'm going to have one stress that's just px divided by cross-sectional area, or px divided by pi c squared. Does that make sense?
Yeah.
Okay. Now the other, and so we're not doing any that, and so I guess I did do the algebra in words, all right, but we're still just talking through things. The other contribution and we went over this kind of briefly, but we were running a little bit out of time, and it's my fault, time management, is that this px does contribute a moment, right, with this little b that we see here, right? So it's going to be essentially causing a torque, kind of around here like this. If I were to draw like this axis here, right? And that you can think of as, being kind of at the end of this beam. So that torque, all right, that has quantity of pxb, right? Now, this px does not contribute a torque. You might think, oh, does it contribute a torque pxa? No, it doesn't, because again, px and lowercase a are in line with each other, right? So r cross f would just be 0. So it's really, you've got this moment that's being applied like this on the system pxb. Now, that moment, let's say I apply here, what is it doing to the stress, the state of stress at A? So remember, like I'm coming down and I have a screwdriver and I'm twisting it, right? What kind of stresses could it be inducing on A?
Shear.
Okay, so you could have some type of shear stress along a beam, right? Even if it were there, though, okay, with this bending moment, the way it's being applied, it's at the top of the. So now we have to look at it as. Let's come over here. If I look at this section of the beam, right? Sometimes it's good to do 2D drawings. Here's my point A, right? This is the wall over here.
Oh, it's at the top and not on the side of it?
So I have to, the way this moment is being applied, I'm looking down at it. I have to think downward. I'm projecting down onto this thing, okay? And so this is kind of like a top-down perspective, and this is the moment P lowercase x B that's being applied at the end. Okay, do you see that? So with a transverse shear stress, because we know that transverse shear stress is maximum at the neutral axis or on the longitudinal axis, and it's a minimum or 0 at the top, at the surfaces, there's no transverse shear here, at least from this px, all right, for multiple reasons. But the other reason is if I look at this pxb here, okay, and I do the external equilibrium on this, so let's say I have a reaction force RR, and I have, so if it's being twisted this way, then I'm gonna choose to do like an R here, like this, right? And then on this side I have the PXB. There's actually no shear in this thing. Okay, there's no, because RR is going to be equal to 0. Okay, so if for another reason, there's no transverse shear stress, right? Because there's no internal shear force along the beam. So, not transverse shear stress, essentially. Okay? No transverse shear stress. But what is there, for sure, from PXB? What kind of stress could it be contributing? Just think about it from this way. Now we're looking down. Here's the P lower subscript XB. P sub XB. What stress could be that adding to the system? Shane?
Compressive.
Yeah, it's a compressive bending stress, right? And and you're absolutely right. It's a compressive normal stress, and we usually say bending stress because that indicates it's coming from an internal bending moment, right? So that internal bending moment is going to have this magnitude pxb all along it, all right? Because if I do a division, if I slice it internally, okay, like say I slice it here now. So this is A, right? And I have an MR on this side. Now the MR is just equal to PXB. All right, I know this is very scribbly scrabbly. Okay, and this is the internal bending moment, like that. Okay, you can see that the internal bending moment anywhere along this beam with this orientation that I've picked from the top down perspective is going to be equal to PXB. Okay. Andrew, there's lots of food here if you'd like some extra. You already got a lunch, but this is you have what? Chicken, tandoori chicken, and a paneer rolls. So anyway, so what we're looking at here is that there is a contribution of bending stress, and it's going to be compressive. Why is it compressive? It's compressive because one, it looks like it's compressive because I'm twisting it like this. But it's also compressive if I just look at the math. The math says that I have minus my over I. Well, if I am coming in, looking at this location, right, I have a positive y, okay, which is just going to be c, right, because that's the radius. So y equals c, and m we said is pxb, p sub xb. So they're positive, and then I is going to be positive as well. So the sigma is going to be negative. All right. So anyway, that's that. So what we can say here is that the sigma x contributing there is going to be this px divided by a, which we talked about earlier, right? That was the normal stress. And we're going to have a negative bending stress, the p sub x b times the radius over I. Okay? And since this is a circular cross section, we can say that I would be pi over 4 times c to the fourth. Okay. Now let's start. So let's erase all this stuff now. All right. So you got that. And let's start looking at. I think I erased everything. Okay, good. Let's look at what's happening from Py. Oh, I didn't erase everything. Py is this force, and yes, it has a moment arm lowercase b, all right, of length lowercase b, and that's causing us to twist like so. Okay. So twist means torsion, means shear stress. Okay, and we so that can be sometimes I'll write tau sub t, okay, because that's torsion. If it's a transverse shear stress from a beam, then I will usually write tau sub v, because the v is what we associate with the internal shear force in the beam. Okay, so the tau t that we have here, that is going to be our torsion formula. That's the Tc over J, Tc and J. Okay. So with Tc and J, what is the T here? What would the torque be? Yes, Andrew.
Py times.
Yes, absolutely, right? P sub y times b. That's going to be the torque that's being applied. And the C, yeah, come on in. If you like some lunch, there's some lunch.
Okay.
Okay. Oh, all right. Thanks for. Yes, it's an unexpected crowd. And, the lab people can go if you want. You don't have to stay here. But yes. All right. See ya. You can also take a little more food if you want, and we'll leave a little food for the class. See if anybody wants anybody. But that's good. Okay. So thank you for bringing the food for us. Appreciate it. Did Praj go by himself?
No, we all went.
You all went? Well, not James. James was here. He was like, "Where's the food?" It's okay. All right. So, so here we have our C, which is just going to be the C for TC over J, and the J would be the pi over 2 C to the 4. Okay, because it's the polar moment of area. Okay, so that's that's the direction it's operating, and this is the expression. Okay, does that make sense? Now, if we think about moving py over here, let me move the arrow. Right? So now let's say that py is operating at this location. What is it doing? What could it be contributing here? With like now the way I look at it, okay, is I look at it as I'm looking at it from the side. This is the wall. This is Py as an external force. Okay? And where is A? A is like over here, and this on the neutral axis. Okay. So the question is, in this configuration, what is Py doing to the state of stress there? Yes.
It's definitely a bending moment.
Okay, so it's applying a bending moment. That's truth, right? So a good way to do this is to take a look at the internals, okay, after we do the externals. So we do first reaction forces, right? So I'm going to choose a smart reaction force, right? We'll call RR going down. And I'm going to also call, like this, a MR, okay, against my PY. You see that? Because PY is going to want to twist, twist is not the right, it's a completely appropriate word, but it wants to apply a bending moment, right? So that it's going to come up like this. So I'm going to apply a restricting. Constraining bending moment on the other side. Okay, so MR, okay, is going to be reacting against this, whatever that length might be. Okay, and RR, okay, is going to be causing there to be a RR is just going to be equal to PY, right? So that's PY. And if I take an internal slice, okay, I have RR is equal to PY, and I draw the internal bending moment and stress like that, okay? Then I see that I've got a internal bending stress, V, that's equal to RR. And RR is equal to PY. So V is operating upward. Okay. So V is equal to PY at that location. Right? Now, I'm going to skip trying to figure out what MR is here, because where is A located? I'll just look at it on the neutral axis, right? So even if there is a bending stress there, or even if there's a bending moment applied, or there's an internal bending moment, better said, the amount of bending stress I have is 0 because I have minus my over I, right, where y is equal to 0. So there's 0 bending stress. Okay? So bending stress is out. What about the shear stress, though? In a beam, right? So in beams, right, we have transverse shear stress and we have bending moment, right?
first off, is there a transverse shear stress? Why?
I mean, I can kind of visualize it, but, also in the internal force, it says P equals Py, so there has to be.
Yeah, we've already determined there's a V, right?
Yeah.
Where there's a V, there's a potential to be a shear stress, right? Because V is shear force, therefore it could be a shear stress. Where is the shear stress maximum on a beam? The neutral axis, right? On the longitudinal axis, right? Depending on whose terminology you want to use. Okay, so it's on this neutral axis, and it's going to max it out. Okay, so if that's the case, then I can think, oh, well, I know that my shear force is Py. I could do a whole blast of V quit, right? But I don't really want to do V quit. I just know that it's a max. And the max, right, for shear stress on a circular cross section, all right, is 4/3 times the average, right? And we derive that in the notes. So here we have a tau av. Now, something to think about. Which direction is this tau transverse shear stress operating? Up. It's in the positive y, right? Because y, it's in that direction because v is in that direction. Okay? The transverse shear stress tracks the direction of the internal shear force. Okay? So with that said, v is upwards in the y direction. So in fact, and then you're going to see in a second, it's going to be called tau sub v because that's what I use for transverse shear stress. That's going to be going up. Okay? So look, here it is. Tau v, all right, operating upward, and it's 4/3 tau av. And tau av is just Py over A, and in this case, A is pi c squared, okay, because c is the radius. So that's the answer. All right. Any questions on that? Piece by piece by piece. All right. It's almost like you have to draw. Every one of these contributors is a different. Yes, Shane.
So which circuit y, z, tau y, z, that, like if you sum those together?
Say that again. I'm sorry.
Like which, if you were to like fill
Yeah. So the total is the total tau there, and you're absolutely right. This is on the x phase.
Yeah.
It's an x phase and it's in the y direction. Right? So this would be another, so the total tau subscript xy would be tau v minus tau t. Does that make sense? All right, and that's like on the next page. Okay? But that's absolutely right. Okay? Now let's look at the contributions, and that clock, okay, good. We still have a few minutes before class, so we're tracking okay. So now let's I'm going to erase all this. And anyone who's walking in, right, you can watch this later if you like. I do think this is very important that we be able to do this because we have a whole section on combined loading. And that means it's potentially interrogable. Is that a word? You can be interrogated on it. Okay. On Monday. So let's look at what's happening from PZ. So PZ is coming through here, all right? And, it's kind of, we can see that it's going to contribute a bending moment with PZ times A, right? We don't care. We already said this like 3 times. PZ is in the same direction as the lever arm with the lowercase b, right? So R cross F is going to be 0 there. So it contributes no moment based on the length b, lowercase b, but it does contribute based on lowercase a. So we have some moment being applied there, okay? And so let's look at it. If I look top down, okay, on the system, I can say that I've got essentially this external PZA. Okay, that's like a moment that's acting on it. And I also can say that if I move PZ to this intersection, right? This would be a PZ acting like that. I also kind of have this PZ external force acting on the system. Yes, Andrew.
So is that like a top-down view?
Yeah, exactly. So we're looking at top-down view, right? Which means that A is in the middle. Capital A is in the middle. Okay? And this is top-down. So top-down would mean that I've got X in this direction, and we got X, Y coming out of the board, PZ, let me make sure I got this right, and then this would be the Z direction. Is that right? X, Y, yep, right hand rule. This is Z.
Wouldn't they still be on the top then?
Hmm?
Wouldn't the point A still be on the top then?
Oh, yeah. Thank you. Yes. Sorry. Yeah. Okay, so A is up there. Thank you. Okay, so now I've got this external load on it, and we can kind of do a couple of things. We can take a slice there, and we can look at the internal shear force and the internal bending moment, okay, at this location. And this is A, all right? And we've got this external one, and we've got this external one like that, okay? So I know it's really messy. I appreciate your patience here. Does it let me? It's not gonna let me. All right. So with this system as it is, what is the moment? Let's look at the moment. What's the moment going to do there? The PZA moment in terms of the stresses at A. Yeah.
It's a compressive normal moment.
Yeah, it's a compressive bending stress. I agree it's normal. Bending just specifies that it's because of bending, right? It's doing the same thing that PX did, right? Except the quantity of that moment is different, right? PX was PX times B. This is going to be PZ times A. All right? So it's contributing a bending moment. It is not contributing, PZ does not contribute like an axial normal. It's not along the beam type of force, right? But it does have this PZ, okay, which would be contributing an internal shear force, okay? And at that location, A is at the outside it's on the top of the beam, right? So that means that the transverse shear stress at the outer surface is 0, right? We know this, well, if you do VQ over IT, right? We know that there's like no Q there because it can't go above it. Okay, so that's going to be 0. So this can contribute a bending stress, or sigma x, right? That's going to be compressive. All right, so that's going to be the PZA, right? And it's going to be negative, right? So because it's negative my over I, y is equal to c, and I is equal to pi over 4 c to the 4th. Okay? So if we go on with this, we get the PZA times c over I. There's no transverse shear, okay? Because a prime is equal to 0. If you're looking at v over I. Welcome. If you like, there's some food here, Joshua. There are rolls. There's tandoori chicken on this one, and there's paneer on the outer one. If you like. Okay. So yeah. So we've gone through and we've kind of knocked down these different things, and those are the napkins. That big roll is a napkin if you want it. But yeah, they have those things. Yeah. Oh, sorry. Did I not offer you? I'm sorry, Kavya. Oh, Dylan, I did offer. I'm sorry. Yeah, there's food. There's food. We this is not how we normally do office hours, but I had double booked myself, and I told the lab we were going to have lunch, and I told you I'd be here, and so the lab actually came, and they joined us for a little bit. It's kind of a sad way for them to have lunch, actually, but I don't know. Like there's a story. I believe he's now passed, but Professor Bose, Bose speakers, right? So he was a professor at MIT. So I had friends that like took his exams, and he would bring ice cream to the exams. They had ice cream. I don't know if this is true. So someone on the internet can verify this, all right? And my friends told me that you never saw a more depressed-looking group of students and people eating ice cream together. Because they couldn't talk to each other, and they were like in the middle of the exam, and they had there was no time limit either, So they just they could eat their ice cream and work on the exam. Anyway, sorry. That's we're not going to have ice cream on Monday, all right, for the exam. Sorry. Okay. Anyway, so. The next slide is all about doing the more individual pieces of algebra that we were talking about, okay? And adding them together as you're putting forth. So area is pi c squared, I is pi over 4 c to the 4th, j is pi over 2 c to the 4th. My mnemonic here, at least when it comes to cylindrical cross sections, is that it comes before j, and so it's smaller. But A does not apply to that, okay? I think you know what the area of a circle is, okay? So that I don't, it doesn't go in alphabetical order completely from A to J, right? But I comes before J, and it's less than J is, okay? All right, so as Shane was getting at, we want to be able to add some of these, you see there's 2 shear stresses right here, okay? And we want to be able to add these components to each other. And we also want to be able to draw the state of stress, okay, that exists at this location A. So you see, going back to and I'm going to erase this, otherwise I'm going to have a messy slide, and I'm going to forget to do it later. And so I'm just going to erase all this. I know. Okay. But you see the coordinate system that we have chosen here, that this is x, this is y. So x was coming out of this pizza, right? This is the pizza, and y was coming, x is coming out of the face of the pizza, y is going upwards, all right? So here, when we go to this next slide, we still have these elements, and we've kind of tried to draw the stresses here, okay, in terms of which directions they're operating. And now I'm going to make an element, and you see x now is going to the right, and it's coming out of the page here. Y is still going up, all right? And I've just drawn A inside the element. So now, right, you see sigma x we said was in the x direction. That makes sense, right? So I can think about drawing sigma x, right, on either side, like this, okay? And the transverse shear stress and the torsional shear stress, we ended up saying they're happening in tau xy, okay? A few minutes ago we drew this out. They're happening in tau xy, And so now let's go ahead and follow our convention. We're just drawing, this is just a standard conventional way of drawing the normal and shear stresses on a 2D element. Okay. So to make it in equilibrium, all right, so tau xy is the one I always start with. It's on the positive x face in the positive y direction. This is this is tau y x, right? And we know that they are going to be equal to each other, and they counteract like that. The arrows meet each other, and then we have their corresponding pairs on the minus x face over here and on the minus y face there. Okay, so we've nothing here but just draw the 2D state of stress on a 2D element. And now we can go ahead and start adding things together. So we can start putting everything together. So we have sigma x with this equation, right? But we also have a sigma x from this expression down here. Okay? So now all those sigma x's add up to each other. Add up with each other to create the combined sigma x. Similarly, we said before we have these tau t and tau v. Okay? So tau xy, now this is maybe a little bit tricky. Which one of these is positive? Tau v, right, is the positive one, right? That's going to correspond to tau xy, whereas tau t from transverse shear stress is actually going in the opposite direction. So here we have tau v, and then we do minus this one right there. Whoops, okay, and that's the complete state of stress. That's the complete state of stress for this structure. Is this a hard problem? Yes. Would I give you 3 forces at the end of a right-angled beam? Probably not. Would I give you 1? Oh yeah. Okay. Could I apply a moment on the end of a beam, or on the end of a cylindrical shaft, you could say, which is also the one acting as a beam? Oh yeah, that was on the homework, right? So yeah, you know, but this is kind of to demonstrate all these compounding things. And we're taking advantage of superposition, right? That's what we're taking advantage of. All right, I'm going to stop the office hour because we're actually now late for the regular class, and then we'll get to the regular class. But any questions before we move on? Yeah, Shane.
Why isn't there shear stress from PC?
Okay, from PC. Okay. Yeah. Okay. There is a shear force from PZ. Do we agree on that?
Yeah.
Okay. There's a shear force from that, but because if I'm looking top down, and you know, I messed it up once before, but I'll try not to mess it up this time. So if I'm looking top down, right, and I've got PZ acting like this, okay, and we agree A is on the outside of it, on the top. I'm looking top down. It's because it's on the outside. That's why there's no shear stress.
I was
Right.
getting the 2 different shear stresses confused. But
Yeah.
One 0 in the middle, the other 0.
Yes. Right. So, yeah. All right. I mean, this is worth writing on your formula sheet. Bending stress, maximum at the top and bottom, or you know, on the outside of the beam, right? 0 on the neutral axis. And you could just write down sigma equals negative my over I for that, because you can see y, right, is going to be sigma is going to be maxing out when y is maxing out. And that's another thing that people often get confused with is, oh, my over I. What is the I? I is just for the entire cross section, right? Because then they think of V quit for the transverse shear stress. And yes, V quit, so VQ over IT, I is for the entire cross section. T is for the entire cross section. Q, not so much, right? Q is the nasty one. That's the integral y prime dA prime, that mess, right? So in that case, though, the Q is equal to 0 whenever the point of interest is at the top or the bottom. Okay, so that means that the transverse shear stress is 0 at those locations, but it maxes out where you get a maximum Q, and that's when it's at the neutral axis. Okay. So yeah, that's and and I'm not too cruel. I mean, I might do some problem. It's actually been a while, I think, since I made someone actually do the integral for VQ over IT. Maybe we should do that on Monday. I don't know. But for sure, I like to say, what is the shear stress when it's at the neutral axis or when it's at the outside? Because it's either 0 or max. And if it's cylindrical, the max is 4/3 tau average, and if it's rectangular, it's 3/2 tau average. Right? So you can just kind of run those things. Okay. Let's. Any other questions for office hours? That was. In some ways, actually, hold on. I wanna. Oh no! I can't cancel. I wanted to erase that. Oh well. I'll keep it, but then I'll have to erase it later. In some ways, that was kind of cathartic. I was like, got to, because we rushed through the last one so fast that I didn't get a chance to really like explain this.